just want to make sure you can hear me clearly and you can see the PowerPoint that I'm sharing. Okay, good. Right. Okay, good morning, everyone, and welcome to Lecture 9 of 124103 Biophysical Principles. The topic for today is torques, but it's still related to what we've been talking about. So just a recap of what we've been talking about. Last time we talked about forces. So we said that force is what causes an object to accelerate or to move from rest. And so if you have a net force that's equal to 0, that means that acceleration is 0, meaning the velocity is constant, the speed and the direction does not change, right? So that's what we've learned last week. We've learned that if the net force is equal to 0, then the acceleration is 0, and therefore the object will move with the same speed and in the same direction, or it will remain at rest if it's already at rest. And if the net force is not 0, then that net force will cause the object to accelerate. So aside from causing an object to accelerate, the net force, a force can also cause an object to rotate, right? So say, for example, I have a pinwheel here, and if I exert a force, we define force as a push or pull on an object. So if I push downward on this pinwheel, so we know that, and we can observe that the pinwheel will rotate. So force, aside from causing an object to accelerate, force can also cause an object to rotate. Okay? And that is torque. Torque is the tendency of force to cause a rotation in the object. So for example, this is a door hinged on one end. If you push on the door on one side, then that force, the push that you've exerted, will cause that door to rotate. And that tendency of that force to cause this door to rotate is what we call torque. So torque is represented by this Greek symbol tau. Okay, so it looks like a fancy letter T. Okay. We read this as tau, and that represents the torque or the rotation of the object. So the unit for torque is Newton times meter. It's a derived unit, and we'll look more into that, why it's Newton times meter. We'll look into that now. So you can see there, Newton is the unit for force, right? So obviously torque should be related to force because it's the force that causes an object to rotate. And if we think about torque and the rotation of the object, the torque will depend on 3 factors. It's the magnitude of the force. So of course, if I push on this pinwheel with a small amount of force, so if I push lightly, the rotation will be small, right? As opposed to when I push hard, then the rotation, you'll have a bigger rotation, and therefore a bigger torque, and therefore a bigger rotation. So the torque or the rotation will depend on how hard you push or pull, meaning the magnitude of the force. So that's the first factor there. It also depends on the direction in which the force acts. So obviously, if I push downwards on this side, then the pinwheel will rotate, from your point of view, it will rotate anti-clockwise, right? If the force is exerted downwards on this side, then the pinwheel will rotate anti-clockwise. If I push upwards, okay, if it's an upward force, then the pinwheel will rotate in the opposite direction, clockwise, right? So the rotation and the torque will depend on the direction for which the force acts. And then the third factor is the point at which the force is applied on the object. So notice how if I push on at the end, okay, I hope you can see the video quite clear. That's why I'm using the white background there. If I push downwards here, the pinwheel will rotate. But if I push in this direction, yeah, I push in this direction, then the rotation, yeah, it won't rotate. As opposed to when I push directly downwards, like so. So the point at which the force is applied also affects the torque and therefore the rotation of the object, right? Okay, so putting these three factors together, putting these three factors that affects torque together, we can come up with the equation for the torque, which says that the torque is equal to Rf sine theta. So F is the force measured in newtons. Okay. Yeah, as we've seen earlier, the torque and therefore the rotation depends on the force, how hard you push or pull on the object to cause it to rotate. The sine theta in this equation tells us about the torque depending on the direction for which you push or you pull on the object. And I'll talk more about this sine theta in a moment, but usually this is the basic definition for torque. But when we start to analyze torque, this sine theta we won't really use it often. We'll use the form where, yeah, the sine theta sort of indicates that a force that's perpendicular to the moment arm is what affects the rotation of the object. Yeah, okay, so for now, we will go through each of those in a bit because there's some terms that we need to introduce. But for now, F, that's the force that will cause the rotation. Sine theta embodies the effect of direction for which the force acts. And then there's this R. So this R embodies the point at which the force is applied to the object. And the R is called the lever arm or moment arm. Okay. The lever arm or moment arm is the distance that is measured perpendicularly from the force to the pivot point of rotation. So the pivot point of rotation, it's that point about which the object rotates. So for the spin wheel, the object rotates about this point in the middle. Okay, so this is the pivot point of the rotation in the pinwheel. The moment arm is measured, the moment arm or lever arm R is measured perpendicularly from the force to the pivot point. Okay, and that's why the point at which you apply the force on the object matters, because if you apply the force perpendicularly downwards, then your lever arm is measured from this force here to the pivot point, that point where your object rotates. Okay. So this is the lever arm. This distance, bounded by my two fingers, is the lever arm when you apply the force perpendicularly downwards in this way. Whereas if you apply the force, I hope, you can see that. Whereas if you apply the force this way, okay, then the lever arm is 0 in this case, because then your force directly goes through the pivot point, and that does not produce some rotation in the pinwheel. Right. Okay, does that make sense? What the pivot, what the lever arm or moment arm is, and how you determine it? Okay, yeah, good. All right, we will be determining the lever arm a lot when we want to determine the torque on the objects. So there will be a lot of opportunities, and we'll see a lot of examples of how we determine the lever arm. But for now, we're just defining the lever arm. It's that perpendicular distance from the line of force to the pivot point of rotation. And it has to be measured in meters because it's a distance kind of thing. And it's really important that is measured in meters because the unit for torque, torque unit as shown in the previous slide is Newton times meter. Right, so your lever arm gives you this meter and the unit for force is Newton. But remember that Newton is a derived unit. It's kilograms times meters divided by seconds squared. So inside of the unit Newton is this meter, and that's why your lever arm has to be measured in meters, right? So if you're given a lever arm in centimeters, for example, in the question, in the test question, or in a problem, worded problem, then you must convert your lever arm from centimeters to meters, right? Okay, so these figures illustrate how we determine the lever arm, which I sort of briefly demonstrated with the pinwheel earlier. Okay, so say that's the pivot point there, a hinge, and the door can rotate. If we apply the force perpendicularly on this end of the door, you measure the lever arm as the perpendicular from the distance from the force to the pivot point, and so this will be the lever arm for this force. Yeah, so if you extend, if you can extend the line of force, and then if you draw a line that's perpendicular to that force and passing through the pivot point, then this will be the lever arm in this scenario here. Okay. Right, and so we can see also from the demonstration I did with the pinwheel that only the force that's perpendicular to the lever arm contributes to the torque. Yeah, because then this is the force is upwards. Yeah, this is the upwards force, and your lever arm is here. That's the lever arm of force A. Notice the angle they make together is 90 degrees, so they're perpendicular to each other. Whereas if you apply a force here, and your lever arm is parallel to that force, then this force will not be able to rotate the door, right? So it's only the force that's perpendicular to the lever arm or moment arm that contributes to the torque and to the rotation of that object, right? Now the question is, what if the force is applied diagonally? Okay, so say with the pinwheel demonstration here, instead of pushing vertically downwards, right? Yep. I angle my fingers so that I'm now pushing diagonally on this end of the pinwheel. So how do we deal with forces that are diagonal to the object? How do we find the torque? How do we find the lever arm? Okay, so one method is to extend the line of force, because remember, you need to find the lever arm, that perpendicular distance from the force to the pivot point. Okay, so if you have, say, this diagonal force FC, then what you can do is to extend this line of force so that you are able to draw this perpendicular line that goes from the line of force to the pivot point, and that determines the moment arm. So RC is the moment arm for this perpendicular force FC. You notice how there's a 90-degree angle between the extended line of force and the moment arm RC. All right. Okay, so that's one way of determining the liver arm. The other way of determining the liver arm is that, remember, if you have a diagonal force, yeah, and we've learned this last time last time when we were talking about diagonal forces, remember that your diagonal force can be broken down into a horizontal force and a vertical force, right? And notice how your horizontal force goes directly through your pivot point. Your moment arm is 0. So this horizontal force doesn't contribute to the torque, whereas the vertical component of the diagonal force is actually what will contribute to the torque. So the second method is that when you have a diagonal force, then you can get the X component or the horizontal component and the Y component or the vertical component. And notice how the horizontal component is parallel to your moment arm. It goes, if this is the horizontal component that I'll just copy up here, that's the FCX, the horizontal component of your diagonal force F. Notice how it can go directly through the pivot point, and therefore the horizontal component does not contribute to the torque, whereas the diagonal or the vertical or the Y component is exactly the same scenario as FA, right? You can extend that the line of force of the Y component, and notice that you can have this perpendicular distance between that Y component and the pivot point, and that's the moment arm for the Y component of the force. All right. Okay, so if you have a diagonal force, yep, you can break that down into the horizontal and vertical component, and only the component that's perpendicular to the moment arm contributes to the torque. Yeah. Right, and so let's go back to the equation for the torque. So that's what sine theta is all about. Okay. Sine theta actually means here that only the perpendicular component of the force perpendicular to the moment arm is what contributes to the torque. So force and moment arm or lever arm should be perpendicular. Perpendicular to each other. Okay. So that's what sine theta means in the equation. And so usually when we solve for torques, we don't have to worry about that sine theta if we're breaking down the diagonal force into its horizontal and vertical components. And so the typical equation that we'll use is this: torque is equal to R perpendicular times F. Yep, so this symbol here, that symbol means perpendicular. Okay. So that reminds us, that symbol reminds us that the moment arm and the force should be perpendicular to each other. Okay. All right, does that make sense so far? Or yeah, if you have any questions or anything is unclear, just feel free to pop it into the chat box. Yeah. Okay. Are we okay so far? Can we sort of follow the discussion so far, and we can move on? Okay. Right. Good. There's some I can see some thumbs up there, so I think we can move on. All right. Yep. So So we can see there the lever arm also depends on where the force is applied. So we can see if the force is applied perpendicularly to your object, then you have the full maximum lever arm. If your force is applied parallel to this object that's supposed to rotate, then your lever arm is 0. So it depends on where the force is applied, and it also depends on where the direction where the force acts. Yeah, we've seen that for when the force is perpendicular to the object that rotates, then you have a different lever arm compared to when your force is diagonal relative to the object that rotates. Okay. And as I've demonstrated earlier, your rotation can either be clockwise or anti-clockwise. And we distinguish between clockwise. Yeah, we'll look at examples, Oksana, like examples with numbers later on, and hopefully that will clarify how to get the moment arm. Yeah, so we've seen that the rotation can either be anti-clockwise or clockwise. And to distinguish between clockwise and anti-clockwise rotation, we use signs. Okay, so here we will use the convention where anti-clockwise rotation means positive torque. Or I guess it's the other way around. If your torque is positive, that means it will cause an anti-clockwise rotation. And if the torque is negative, that means it will cause a clockwise rotation. Right? So for example, so for example, I don't know, can you see? Yeah, hopefully you can see the video here. So for example, I push on this end, right? So will the force provided by my push force in this on this end of the pinwheel, will this be a positive torque or a negative torque? So there's a downward force on this end of the pinwheel. Do you think this will give you a positive torque or a negative torque? Yeah, right? Okay, good. Negative torque, because the tendency of this downward push on this end, the tendency is to rotate the pinwheel in a clockwise direction, and therefore the torque that is provided by this downward force should be negative, right? Yeah, right. Okay, so yeah. So for forces, when we were talking about Newton's laws and net force equals 0, we said that if the force is pointing downwards, that's a negative force. And putting the sign of the force is important when we're getting the net force. Okay, so the fact that torque can also either be negative or positive sort of gives you an idea that later on we will be looking at net torque. And when you're finding the net torque or the total torque that's introduced by all the forces acting on the object, then it's important to consider whether that's a negative torque or a positive torque. Yeah. And if the torque, the tendency of the torque is to cause a clockwise rotation, then that's a negative torque. And otherwise, anti-clockwise rotation is a positive torque. Right. Okay, so here's an example for determining torques and moment arms. So here you have wrenches. In the first case, you're pulling on the wrench with this diagonal force with an angle, so that you have this diagonal force. And then on the second case, you're pulling directly upwards on the wrench. And then on the third case, you've decided to extend the handle of the wrench so that, but you're still pulling directly upwards on the wrench here. So the question is, in which scenario will it be easier to rotate the wrench? Is it the first, second, or third case? Yep. Good. I can see a question there, the answers there in the chat box. Yeah, the third scenario will make it easier to rotate the wrench. Okay. For the first case, so assuming that the same amount of force is applied. Okay, assuming same amount of force. Okay. The amount of rotation now depends on how long the moment arm is, or the lever arm is. So for the first case, right, you extend the line of force and you draw a line perpendicular to this force and passing through the pivot point, and therefore this is the lever arm. It's this distance. Okay. This distance between the pivot point and the point where you have this perpendicular angle with the force gives you the lever arm in the first scenario. In the second scenario, right, the force is being applied perpendicularly to the handle of the wrench. So this distance between the force and the pivot point, this is the lever arm, R. Okay. So just roughly comparing the length of the lever arm in the second case and the first case, you can already see that the lever arm in the second case is longer, right? And if you extend the length of the wrench, the handle of the wrench, and you're still applying the force perpendicularly to the handle of the wrench, then of course the lever arm will be longer in this case. So notice how your lever arm is perpendicular to the force, okay, and it's passing through the pivot point. Right? Okay. Right. So the longer the lever arm for the same amount of force will give you more rotation because you have bigger torque. Right. So I hope this example clarifies somewhat how you find the lever arm, because yeah, that's one of the important things is to find the lever arm. Whenever we're talking about torque, it's really important that you're able to find the lever arm because that influences how much torque the object experiences. Okay. Right. Are we good with lever arm and torque at this point? Right. Okay. Yep. Okay. So maybe we can move on. All right. So we've now seen that force can either cause acceleration if the force is non-zero, if the net force is non-zero, or force can cause rotation on an object. So now we will talk about stability and equilibrium for an object. And when we're talking about stability, of course, in real life, objects are extended. They're not points or dots that we can easily treat. So we will be looking at extended objects. And when we're looking at extended objects, it's quite difficult to analyze forces through an extended object and torques through an extended object. This pinwheel demonstration actually shows us that actually this is an extended object, but its rotation is just about a single point, which is the pivot point. Okay, and so we will consider what we call center of mass. The center of mass allows us to sort of shrink the extended object into a single point, and that makes analysis simpler because then we're just looking at a single point instead of looking at the whole extended object. So the center of mass, it's it's the point where we can consider the object to be just a single point and forget about all the extensions there. It's that point where all the mass that makes up an object is concentrated. And that's why we can consider it as a single point, because say the whole mass of this thing is concentrated at this point. So we'll just look at the effect of the force on this single point, acting about this single point. Okay. So how do we find the center of mass? A center of mass, okay, is that point where you can balance the object. Okay. So we know, for example, this pen. Okay, if you try to balance it at either end, you know the pen will fall, right? Will fall down. The pen will not balance, and it will fall down because you have this torque, this gravitational pull on this one end that will pull this object down, this pen down, that will cause it to rotate. So balancing this pen at one end doesn't cause any stability, doesn't bring any stability. But we know that if you balance it somewhere in the middle, then that the pen is stable if you balance it about the middle. That point where you're able to balance that object is where the center of mass is. So it's as if all of the mass of this pen is located at this point, such that if you balance this object at this particular point where all of the mass is located, then it's as if you're supporting the whole mass of this object at that point. And therefore the object is balanced. So that point is called the center of mass. That point where you are able to balance that object is called the center of mass. Okay, and the center of mass is an important concept, for example, in designing toys. So this dragonfly here it's an extended object, but if you want to find the center of mass of this dragonfly, you need to find that point where this whole thing balances, where you can balance this dragonfly, right? So it balances at the beak. I hope you can see that. Yeah, try to bring it closer. Right, so that means the center of mass of this dragonfly is at its beak. Well, dragonflies don't have beaks, but it's at this point, right? It's at this point where it's balanced. And if you try to balance this dragonfly at any other point, well, it will just fall. Yeah. Okay. And the reason why it balances at this point is it's the mass is concentrated at that point, such that if you support the dragonfly where all of its mass is concentrated, then you have stability, and you're able to balance this thing. All right. Okay. So does that make sense? Does the concept of center of mass make sense at this point? Yep, good. Yeah, it's that point where you can balance that object. That's where the center of mass is. Yeah, so for this refrigerator, this object here, say the center of mass is at this point. So if you balance it directly above the center of mass, then this object is stable. Notice in the second scenario, okay, the center of mass is at this point. If you balance it here, okay, gravitational force will act at the center of mass. So you'll have a downward gravitational pull, gravitational force, and that the tendency of that gravitational force will be to rotate. Yeah, rotate that object in the anti-clockwise direction. Therefore, you have a positive torque in that case. Okay. For this scenario here, if you try to balance this object at this point, the center of mass is outside of where you're balancing it. You have a weight force that will pull your object downwards, and that weight force will give you this torque. Will have the torque that will rotate your object in the anti-clockwise direction. So you have a negative torque. Right, so to achieve equilibrium or achieve stability, you need to support the object at its center of mass. Okay. Right. Now, how do we find the center of mass? We've seen it's where the object balances. For our course, oh yeah, here's a practical example of a center of mass, and you can do this maybe during the break or just before or during the workshop, right? Try to touch your toes and try if you can jump forwards or backwards. You might find difficult. For this case, if you're bent over, your center of mass is around this point. Okay, so try this exercise and try to see if you're able to keep yourself stable by jumping forwards or backwards. In this case, your center of mass is outside of where you are supporting your body at your heels. Okay. You can also do this other exercise later on during the workshop or during the break. Right, so trying to find the center of mass of extended objects is trying to find where that object balances itself when it is supported. For our purposes for this course, we will restrict ourselves to regularly shaped objects for symmetric geometrical shapes, and that allows us to find the center of mass easily. For symmetric objects, the center of mass is at the geometric center. Okay, so if you have a circle, for example, the center of mass is in the middle. Okay. If you have a rectangle, like the pen can be modeled as a rectangle here, and that's why roughly you balance it roughly at the middle. So center of mass is roughly at the middle of this pen, so you can consider it to be like a rectangularly shaped one. So rectangle or square. Yeah. So yeah, we will only consider geometrical shapes, and so the center of mass is directly in the middle. Otherwise, if we'll give you a scenario where it's not a geometrical shape, then we will clearly identify where the center of mass is. Right, so we've been talking about equilibrium and forces. So as I've mentioned earlier, equilibrium is either when you have zero acceleration, your object is either at rest or it's moving with the same speed and in the same direction. Right, and you can only have equilibrium if the net force is zero. We've seen this last time. Newton's laws of motion, we've been learning about the net force, and if the net force is zero, we've learned that the acceleration is zero, and therefore you can have either constant velocity or at rest condition. And the second condition for equilibrium is that the net torque or total torque should also be zero, because then the object will not rotate. So for the first case, net force is equal to zero. That means acceleration is zero. Either object will not move, it's at rest, or it will continue moving with the same speed and in the same direction, or velocity is constant. Okay. Right. So that's why net force has to be zero, but also net torque has to be zero so that there is no rotation. So this one will give you no rotation. Right. Okay, so we will now consider equilibrium scenarios, and here we will look at closely now how to find the lever arms and the net torques. But just a few, so just like in kinematic equations and Newton's second law of motion, solving problems is sort of a recipe that you can follow some certain steps to arrive at the answer. So it's the same thing with torques. So to find the equilibrium condition, so you have to balance the forces out so that net force is 0, and then you have to balance the torques out so that the net torque is 0, which means anti-clockwise torque should be equal to clockwise torque. Yeah, right. Net force is equal to 0 means upward force is equal to downward force, right? Balancing out the torque so that the net torque is 0 means anti-clockwise torque should be equal to, clockwise torque should be equal to anti-clockwise torque, because we know clockwise torque is negative torque, anti-clockwise torque is positive torque, and so they sort of cancel each other out. Right, so to find the torque, to balance out the torques, just like we did with forces, identify the object that will have the tendency to rotate. Draw the free body diagrams again. So whenever we're talking about forces, you cannot get away from free body diagrams, because that is where you can visualize all the forces that are acting on the object. Okay, and to find the torque, you need to find the force and whether it's acting upwards or downwards or to the left or to the right. And then pick a pivot point. That's the point about which the object can rotate, and the pivot point can vary. So this is a personal choice. I will teach you how to choose the pivot point wisely, right? But choosing the pivot point is arbitrary. That's your choice. And then before you can calculate the torque, you need to choose your pivot point, because to calculate the torque, right? Remember, you need the moment arm, multiply that with the force, and to find the moment arm, you need to know where the pivot point is. Because moment arm is the distance between the force and the pivot point. Right, and remember the weight of the body, the object always acts at the center of mass. Okay. Right. Right. And the forces at the pivot point will have no net torque. Okay. So imagine the pinwheel. If this is a pivot point, if you directly push on the pivot point, then the pinwheel will not rotate, right? I think that sort of makes sense. If you're pushing about the pivot point, then the object will not rotate, because you're pushing on the hinge of the door will not swing open or swing closed. Right. And that's why if you have unknown or uninteresting forces like the normal force, then you put the pivot point where the unknown forces act, so that you don't have to worry about the torques generated by those forces, because then the torque is equal to 0 when the force is acting at the pivot point. So that's how you choose the pivot point. Put your pivot point where you have an interesting force, or if you have 2 or more forces, then put your pivot point there so that you eliminate those 2 or more forces. So I guess we need to look at an example for these steps to make sense. Okay, right? So let's look at one that is hopefully quite intuitive. So you have here a seesaw, a plank of wood supported in the middle here. So suppose the boy on the right weighs 50 newtons. Again, when we say weight, it's the weight force or gravitational force that's always directed downwards. So I've already drawn this weight force here on the boy on the right. The weight force is 50 newtons. Okay, the boy weighs 50 newtons. How much does the boy on the left weigh if the beam is to be balanced and the beam is supported at the center? Okay. Meaning the distance, the distance between the support and the buoy on the right is 0.8 meters, and the distance between the support and the buoy on the left is also 0.8 meters. So the distance is the same, right? What should be the weight of the buoy on the left? Yeah, good, right? So just thinking about it intuitively, you sort of, the buoy on the left should have the same weight as the buoy on the right. Yeah, because then the weight force of the buoy on the right, will that create a negative torque or a positive torque? Yeah, this one, the buoy on the right, the 50 Newton weight force on the right here, will this create a positive torque or a negative torque? Yeah, good. Yeah, I can see there an answer of a negative torque. Okay, why is it a negative torque? Right, imagine this is the seesaw. Yeah, the buoy, I have to like your point of view here. This is the right side of the seesaw. Okay, the buoy, the tendency of the weight force is to pull the seesaw downwards, and the tendency is to rotate the plank or the beam in a clockwise direction. Yeah, very good. Yeah, the tendency of this weight force is to create a torque that will cause the beam to rotate in a clockwise direction, and clockwise direction gives you a negative torque. Okay. On the other hand, the weight of the buoy on the left, okay, the tendency of this weight will be to rotate the beam in the opposite direction, in an anti-clockwise direction, and we said anti-clockwise direction will give you a positive torque. Okay. Right? And we said that the net torque should be equal to 0. So you have this positive torque on the left, buoy on the left, okay, minus the negative, minus the torque on the right, because the torque on the right is negative. That will give you 0. Or you can also just intuitively say that the torque on the left should be equal to the torque on the right. Okay, yeah. If we wanted to calculate the torque, so how much torque? Okay, so we know, it should be 50 newtons also should be the weight of the buoy on the left. Right, so if you want to find the actual torque, let's find the torque of the buoy on the right. Torque is equal to moment arm times the force that will cause the rotation, right? Okay, so we know the force is 50 newtons. Because it's the weight force of the buoy that will cause the beam to rotate. It's the weight force that will give the torque that will cause the beam to rotate. So the force in the equation of torque equals R times F is 50 newtons. Now, how do we find the moment arm? Okay, the moment arm, okay, what's the moment arm for finding the torque of the buoy on the right? What's the value of the moment arm? What do you think is the value of the moment arm R for this 50 Newton force, 50 Newton weight force? Yeah, 0.8 meters, because see, this is the weight force, it's directly downwards. The weight force is directly downwards. The moment arm, you draw a line that's perpendicular to the force and passing through the pivot point. Okay. So this distance between the force and the pivot point, this will give you the moment arm, R. Okay, and it's given in the problem that the distance between the buoy and the pivot point is 0.8 meters. Yes, so the moment arm here will be 0.8 meters. So when we find the torque, it's 0.8 meters times the force, which is 50 newtons. Okay, so remember, your moment arm should be meters. Well, it's already given in meters, so we don't have to convert anything. So this will be, no, that does not make sense. Yeah, 40 newtons times meters for the torque. Right. Cool. Any question about the solution? Are we happy with the solution for this? Why? Yeah. Okay. So why didn't we need the weight of the beam? Why didn't we just use, why didn't we consider the weight of the beam, and why is it just the weight of the buoy that's important in this case? Yeah, technically the beam will also experience a weight force because it's an object and it has mass. And so there should also be gravitational force that's pulling down on the beam. But why didn't we consider the weight of the beam in this question when we solve for the torques, for the net torque? Right? Think about the center of mass. Where is the center of mass of the beam? We can assume that the beam is a rectangular plank of wood. Yeah, where's the center of mass of the beam? Where is it located? Yeah, at the pivot point. Yeah, the center of mass is at the center. Yeah, it's at the geometrical center of the beam. So the center of mass is midway. This is where the center of mass of the beam is located. It's as if all of the mass of the beam is located at this single point. Okay? And so the weight force on the beam acts on the center of mass. So if I draw the free body diagram of the beam, the weight force on the beam is at the center of mass, which is the geometric center of the beam. And that is where the pivot point is. Okay? That's where we are supporting the beam. Right? And therefore, the torque due to the weight of the beam is 0 because the weight of the beam is acting directly at the pivot point. And so this is the example where you choose your pivot point so that you cancel so that you disregard any forces that you don't want to consider. Technically speaking, if you draw the free body diagram of the beam, you should also have a normal force, right? You should also have a normal force that's directly upwards, right? Because you have this support that is supporting the beam. And so your beam should also have a normal force or a support force that's perpendicular to the beam, right? So if you draw the free body diagram of the beam, you have this weight force that's downwards and you have this normal force that's upwards. But both of these forces are at the pivot point. And therefore, you can disregard these forces when you're calculating the net torque. Because they're exactly at the pivot point. Okay. All right. Okay, so I hope that makes sense. Now let's look at another example. So for this example, it was sort of intuitive to find the weight of the buoy on the left because the lever arm is the same for both buoys, right? They're located at the same position relative at the same distance relative to the pivot point. And so it was quite intuitive to find the weight of the boy on the left. But what if we shift the position of one child so that the distance between the pivot point and the children are not the same. So one is 3 meters and the other one is 2 meters. The boy on the right weighs 200 newtons. How much does the girl on the left weigh if the beam is to be balanced? And the beam is supported at the center here, meaning it's supported at the center of mass. Right? I'll give you a couple of minutes to sort of try and think about this problem and maybe sort of formulate in your mind how you might go about solving this problem. All right, so the first step is really always drawing the free body diagram, right? But free body diagram of which? What is our object here? Which object should we draw all the forces that are acting on it? Is it the boy, is it the girl, or is it the beam? Which object should we consider when we're drawing the free body diagram? What do you think? What's the object in this case? Yeah. Right, so the problem says, how much does a girl on the left weigh if the beam is to be balanced? Okay. Right, so we want to balance the beam. Okay. And the beam experiences many forces, weight force, it's supported, it has its own weight mass, so it has its own weight force. So you have a weight force that's downwards. It's supported by this support, so it should have a normal force. And then you have the boy and the girl that's exerting forces on it, right? And so it's the beam that we want to balance. Therefore, the object in this case is the beam, because it's what's experiencing all of these forces that could cause it to rotate and be unstable or not in equilibrium. Right, so we draw the free body diagram for the beam. Okay, right, so the center of mass is at the geometric center of the beam. That's where the weight force will act, right? So you have the weight force, the gravitational pull on the beam, the weight force of the beam, which is always directly downwards. You have the normal force that's directly upwards. Okay. Yeah, you have the support that's supporting, so the weight force, and then the normal force there. Okay, now here's the difference when we're talking about torques. Yeah, you have the weight force from the boy on the right. Okay. Notice how I put the arrow signifying the weight force from the boy. I put it a certain distance from the pivot point. So this is the center of mass of the beam. Okay. So when you're drawing the free body diagram to find the torque, you also have to place the forces at their relative positions, okay, as sort of the accurate positions of where the forces are acting at on the objects, because the location of the force is important to find the lever arm, right? We've seen that where the force is acting at is important when you're finding the torques. And so you have to draw the weight force at the sort of approximate location of the boy, so that this is approximately 2 meters from the pivot point. Okay, and similarly, the weight force exerted by the girl on the beam on the left is like approximately 3 meters away from the pivot point, from the support, right? Okay, so your free body diagram will be extended as such. Okay, when you're just looking for free body diagrams to get the net force, then you can just say normal force and weight force of the beam, and then you have the weight force of the boy, and then you have the weight force of the girl. Well, they're not drawn to scale. Okay. But if you're just looking for the net force, then you can draw this free body diagram on the right. Okay, it doesn't matter at which distance the forces are acting at. But if you're finding the torque, then it's important to indicate where the net force, where the force is relative to the pivot point. Okay. Right, and so yeah, the weight force on the boy is roughly 2 meters away from the center of mass of the beam, and the weight of the girl is roughly 3 meters away from the center of mass. Okay, right. Any question about the free body diagram? Because this is the most important step, drawing the correct free body diagram. And I think, yeah, the really key idea is to include the distances in your free body diagram. Okay, cool. Right, now that you have your free body diagram, okay, determine your lever arms. A lever arm is already 2 meters. It's the distance between the boy and the weight of the boy and the pivot point, distance between the weight of the girl and the pivot point. Yeah, right. And then, yeah, you choose the pivot point. We'll choose the pivot point for calculating the torque. Right, choose the pivot point for calculating the point. In this particular example, it was already given, sort of the beam will rotate about the support, so it's sort of implied in the question that the pivot point is where you are supporting the beam, right? Because the beam will rotate relative to that support, which is the pivot point. But notice that because the pivot point is at the geometric center of the beam, that eliminates the normal force and the weight force in the calculation of the net torque, because the lever arms are 0, and therefore the torque is 0 due to the normal force and the weight force. Okay. So now that you've identified the pivot point, you can calculate the torques using this equation. Yeah, that's the equation of the torque. Right? Okay, to balance the beam out, you know that the anti-clockwise torque should be equal to the clockwise torque, as we've seen in the first example. Right. Right, so the net torque, yeah, look at each of the forces. The weight of the girl on the left will introduce a torque. That torque will be equal to the lever arm of the girl times the weight force of the girl. So notice here, torque is equal, from this equation, torque is equal to lever arm times the force. So the torque due to the weight of the girl on the left will be the lever arm of the girl times the weight force of the girl. And that will be a positive torque because the tendency of the weight force for the girl is to rotate the beam in an anti-clockwise direction, giving you a positive torque. Right. Okay, normal force and weight force of the beam, they don't contribute to torques. So next, the weight force of the boy is equal to the moment arm, which is the moment of arm of the boy times the weight force of the boy. But that should be negative because the tendency of the weight force of the boy is to rotate the beam in a clockwise direction, and clockwise rotation is negative torque. And that's why you have this negative torque for the weight force of the boy. Net torques should be equal to 0. Okay, so if you work out the equation, this is your equation, or you can just reason out that the anti-clockwise torque should be equal to the clockwise torque. Okay, and so you can just write down that the torque on the girl should be equal to the torque on the boy. Right, so you can skip this step. I'm happy for you to skip the first step here if you use the argument that the anti-clockwise torque should be equal to the clockwise torque. Then you can just go ahead and write down these equations for the clockwise and anti-clockwise torques. All right, we're now just left to substitute whatever values were given. Right, so we see that the moment arm for the girl is 3 meters. It's the distance between the weight force and the pivot point, the perpendicular distance. That's 3 meters. The weight of the girl is what we're wanting to find. Right, for the boy, the moment arm is 2 meters and the weight is given to be 200 newtons. Okay. So we have to rearrange this equation to isolate the weight of the girl. So if I divide both sides, if I divide the left side by 3, then 3 divided by 3 is equal to 1. And I sort of cancel 3 there. Whatever I do on the left, I should also do on the right. So I should also have to divide that by 3. So weight is equal to 2 times 200 divided by 3. And that gives you weight in 133 newtons. All right. Okay, any question about this example? I hope by looking at this example, I hope by us going through this example step by step and in detail, hopefully it has clarified how you find the lever arm. Firstly, how you draw the free body diagram. Remember to draw, an extended free body diagram showing roughly the positions of the forces acting on the object. Okay. And then assign a pivot point. It's usually where, the object rotates about. If the problem does not explicitly give you where the pivot point should be, then put your pivot point where there are 2 or more forces that you can eliminate so that you don't have to include those in calculating the torques. For example, here, the normal force and the weight force of the beam, we didn't have to include them in calculating the torques because they are exactly at the pivot point. Okay. Right, and then if it's an equilibrium situation, then the torques, the anti-clockwise torque that's generated by the weight, by the force, should be equal to the clockwise torque that's generated by the force. And then that's where you use the equation torque equals moment arm or lever arm times force to find whatever is being asked in the problem. Right, are we happy with the solution for this question? And does it make sense? Yeah. All right, good, right. Yeah, at least more than 1 thumbs up there. So I think that's a good sign. Yeah, so that's that wraps up our lecture. We can go to the workshop. The workshop is a very practical one with a FET simulation. The worksheet is on stream and it will guide you through this FET simulation. Yeah, so you can see here it's balancing the beam. So show everything, show the mass labels of the mass and forces on the objects and the level. And you would want, you don't want any supports at the ends, because what we want to do is balance the beam out, and hopefully through by doing this exercise, you'll get the idea about lever arms and torques and forces in a more detailed way. you'd want to measure the lever arms using the ruler there, right? So I will let you go through the worksheet, let you go through the activity using this PhET simulation here, at least for the first part, and then you can go to the second part where you will try to find the masses of these mystery objects, and then there's a game that will sort of bring everything together, right? So I will let you do that, and then we will meet at 10:30, and we will look at some examples of this simulation, and hopefully, hopefully wrap up the workshop. So we'll go through some of the answers, not all because there's a lot. So we'll go through some of the answers of the workshop at 10:30, right? Okay, so I'll let you do the workshop now, or I'll stop the recording.